Yes, there's kinetic energy.
Alright, here we go.
So, are you guys if you want to do so I'm actually gonna go inside. I'm not going into your skin.
I have to.
Wait. Isn't that why you have like 1,000 classes for Sophia? It's also like in classes. Yeah. Yeah. Wait, what? Because if you have second, you'll be with me and Sophia.
Okay, give this one a shot.
Tyler and Geisha and Shoot. Oh, Tyler's madness behavior.
Ladies and gentlemen, we are into the class. Oh, Lord, what you think?
So bouncing off.
Wait, so are they both
Sir.
going one way?
Yeah, they both go
And so it's a rear
This is
They're going the contrary.
I think it's
Okay, so bus, car, and I went.
It doesn't say that.
Yeah, but
Yeah, okay.
Okay, correct answer is
C.
we're going to go C. Inelastic collision. All right. Next question. Same scenario. What happens to the momentum of the system? Oh, your neighbor? Correct answer is B. Concern. Everybody all right with that? All right. Yeah, both objects are in the system and there are no unbalanced external forces. Okay. So this idea of elastic collision, inelastic collision, this is talking about what happens to kinetic energy, momentum, in any of those scenarios are conserved. It is conserved. Okay. Quick demonstration. If you could pull out a piece of paper that you don't really care about. You could use your lab. It's fine. Lift it up, hold it up just a little bit, and smell.
Yes. Look, you can see the tar marks on it. Yeah. Wow. That's crazy. That's why I don't care about this. I don't even know what this is. Orchid energy. I'm so glad I have not this too. Look how perfect. Online orchid solutions. Yeah.
Oh my god.
That does not sound like you can't.
Okay. So here's the point. For all practical purposes, we would consider this an elastic collision. Okay, but the reality is, at a macro scale in our real life, there's no such thing as a perfectly elastic collision because mechanical energy is being lost to sound and heat. I was a little singed. Okay. Elastic collisions happen at subatomic level, like so electrons coming by each other. But just like in physics, we can pretend to have a frictionless surface. We can pretend to have an elastic collision. So bouncy collisions, we can just say, hey, that's an elastic collision. Good with that? Have a conversation.
But I feel like the second inverse is basically so like number 2 is the reverse. Because that's 1. So yeah.
Well, no, I know.
Oh, okay, yeah, got it. But it's less love. That's about the same thing. Wait, so you can say. And then the I just remember but it's a so like it's like together. Like the ones that sticks within the stuff. I thought it was 2 and 3 and it's not an option. I just don't see it. I know it, but then I always like don't know what to that's not like if they're easy on but like there's one that I feel like the 90 numbers is 90 minus like I was like
Okay, what do you say? Okay, obviously 1 is an answer because it's included on all of them. What is the total momentum of this system? You got mass, velocity, 1 mass, 1 velocity, half a velocity, twice the mass. So the half cancels out the 2.
Why does it have to?
You multiply them. So mass times velocity for momentum. Okay. So when they hit, what's going to happen, because it's a totally inelastic collision, meaning they stick together, the total momentum of the system is 0. So when they hit and stick, they just stop. Same story as here. Correct answer is Dangerous Dinosaurs.
You said it was 1 and 2, so I didn't hear it.
You okay with that? Same scenario. Different question.
I'll check the late.
You like don't know. You know what I mean? My shoulders hurt so bad. And then get home. Just like
Smiley is always.
Tell your neighbor what you think.
I'm thinking, yeah, I agree. You should just like make them enjoy life. So I'm still gonna do it because I can't know what you're saying about survivor. Actually, you should just literally. Like, have you been inspired? I've never just swat it out, right? It's not quite as actually, but I do it sometimes. Here's my thing. And most people do.
Okay, what do you say?
So like,
All right, real quick, is everybody okay with this car gets damaged the same? They're all brought to rest. Okay with that? Okay, so we really don't care. The brick wall, we're gonna say, goes unscathed. Ooh, what hit me? Oh, sorry. Which of these two has more kinetic energy? Tell your neighbor and tell them why. Which one has more kinetic? Which car has more kinetic energy?
You're right.
Correct answer is. Okay, so C is the correct answer. Okay, this has more kinetic energy because your speed is squared. Good with that? Okay, this is why your parents stick you in a big tank of a car versus a little sports car. Okay.
This car right here hit a wall at 50 miles an hour. This car hit a wall at 100 miles an hour. I think the difference is pretty clear. The question is, when we smack two cars together at 50 miles an hour, are they going to look like that? Or are they going to look like this?
That makes sense? Does that make sense? The idea?
From each end of the 1,280-foot track, the identical 1.5-ton cars take off. Both cars cars gain speed as they head headlong down the track towards their head-on collision. Then, as both cars reach 50 miles per hour,
It's about to happen.
the cables uncouple.
What can you say?
What can you say? That breathtaking finale is the final piece of their physics puzzle.
Cars which hit each other at 50 miles an hour look exactly like the car we smacked into the wall at 50 miles an hour. That tells me everything I need to know.
Well, the figures are in. The orange car got 52 G's. The yellow car got 58 G's, which, give or take a few G's, is the same as what we got against a wall at 50 miles an hour.
G wins, and the damage data backs up those numbers. Both of the cars are virtually the same length as the 50-mile-per-hour wall test at 11.5 feet.
Good. All right. So when you get done with the lab quiz, I have a